Hello, this is Principle of Magnetic Field Measurement. I'm Vittorio Basso, so we pass to the second part dedicated to the measurement methods and instrumentation. So this is the third recording out of 4. Now we will dedicate some time to measuring instruments. And here also we want to introduce some terminology. So for an instrument, we will have a resolution with something important, so the smallest change of the quantity that we can cause a detectable change for the indication. So this resolution includes the noise that we can have in our instruments. Then another point is the sensitivity, that is the change in indication corresponding to a given change in the value of the quantity being measured. This is more related to the principle that we use. Since some principle could be very sensitive, so detect very small changes, but then the resolution could be very bad because of noise or because of other issues of badly defined quantities also. Accuracy is, let's say, something more related to the general agreement between the value and a reference that we can have, a metrological reference, for example. Well, and we are talking about a magnetic field, so it's two very important issues are how big is the sensing region, centimeter, millimeter, microns, and if we are able to measure the absolute value or the vector components of the field. This is absolutely an issue to consider because it's not the same. We can take this classification given by Peter Keller when we have a general accuracy let's say as a function of the field. Field have so many orders of magnitudes here, but the point is essentially that the most accurate, as you have seen, NMR and EPR, electron paramagnetic resonance, or nuclear magnetic resonance methods are those that are able to achieve the best accuracy. Much worse if we go down, so we have the flux meter, the whole probe methods, magnetoresistance and magnetoctantance, so effects related to metals in solid state, the fluxigate, an instrument that we already mentioned that we've seen more detail. Squids can go down to the field, but then accuracy depends very much on how they are arranged. Okay, so again, in this part, we will subdivide in two. So let's say methods for the instrument that are used on or equation of electromagnetism, and we include both classical and quantum effects, so also where we use superconductive materials, and several methods and instruments using magnetic materials. And then in part B, the magnetic resonance. Again, they can be used some classical resonance or quantum resonance by using atomic levels. Let's see. Let's start with this recording with these three. Electromagnetism, magnetic materials, and the classical magnetic resonance. Okay, so if we remember the first lecture, we mentioned that if we're able to measure the voltage change on a pickup coil, this voltage change is related to the change of the magnetic flux. So if we want to measure the flux, then we have to integrate in time the voltage. These instruments exist. These voltage integrator are called flux meter. They are commercially available, and what they do essentially, they give a value in volt per second that are really converted in the units of magnetic field, the flux of the magnetic field, and then so the flux of field. The point, they are very good in making this integration. They have very good resolutions, but the sensing region has to be large. So the coil has to be large. and the flux of B must change in time. So either you change the field or you change the position of the coil, and in both cases are used. This is a method which is very much useful for magnetic materials, because then you measure B, not only H. So if we have a pickup coil around a magnetic material, you are able to measure the magnetization changes. But also for the field they have application, and the main application are mainly again with ferromagnets, with magnetic materials. It's not easy to, let's say, define the field which is applied to a ferromagnet, extended ferromagnet, a slab for example. One method is to use, say, the difference in the potential between 2 points. And this difference can be measured by means of a special coil called Rogowski coil. This is the geometry in the plot. Then the point is that you have to carefully measure the change of B in this coil. So flux meter is the instrument that can be used for that. Another very interesting application and very widespread application of flux meter is the measurement of a magnetic moment of an object. For example, in the picture, the person holds in hand a permanent magnet, and you want to characterize the moment that this permanent magnet has. So what to do? One point is to use the reciprocity property of electromagnetism. So if we have a coil, and this coil constant, let's say, makes the relation between the current and the magnetic field, but the same coil, the same constant, gives also the relation between a magnetic moment that is put inside and the concatenated flux. So it means that if we change, I mean, we pass from a situation when the magnetic moment, the sample, is outside the coil, and then you put it inside, you will get a change of phi of the magnetic flux. And then if we integrate, if you're able to measure it, you're able to measure, to quantify the magnetic moment. So this is something also that you can find commercially. So there are instruments to measure, to characterize the magnetic moment based on flux meter and, in this case, Helmholtz coil. So one important instrument to measure magnetic flux is, instead of using just a normal coil, but using a superconducting coil, and not just a normal one, but for example including in the coil a junction, so a Josephson junction. We have many different geometry and many different choices. These instruments using this superconducting coil with Josephson junction are called SQUID, superconducting quantum interference device. And for the RF SQUID, we have just one Josephson junction. For DC SQUID, we have 2, but the point is always the same. That's the flux is quantized inside the ring, and the flux quantum is the one mentioned there, so written there, the Planck constant over 2 times the electron charge. In principle, we can count the flux quantum, and then the quantum flux is the ultimate sensitivity for measuring the magnetic flux, something very nice. So possibly also used in for metrology issues, as H is fixed, E is fixed. The point is that measuring the flux changes could be not that easy. The point is where these squares should be placed in terms of amplification and electromagnetism. So things are a little bit complicated. Just to mention that in one case you have to put, in any case you have to put currents changing, currents, in one case changing in time, in one other case, in the other case no. And then the point of measuring the quantum of flux is just to look at variation, periodic variation, when you change this flux and then you count them. Where the application of these squids are so many, one point is that you have to be at cryogenic temperature, and this makes them not so easy to handle. In many cases, these squids are not directly used to measure the individual flux of the B field, which is concatenated to them, but they are used as amplifiers. This is a very common application, because then you can build a very sensitive methods to measure magnetic materials, essentially coupling a method close to the one seen before with the Helmholtz coil to measure the magnetic moment of macroscopic samples, but then this can be done at very small scale, and also to measure very, very small value of magnetic moment, thanks to the squid method. Leave the squids for the moment and pass to a more common instrument. It's called the flux gate. We have already seen it. So let's spend a minute to look at the measuring principle. So the point is to have a magnetic circuit. So we have magnetic materials. In the picture in the left, you have the two bars. These two bars are made of some soft magnetic material. As you can see, where you have an inner winding of a wire that for the left magnetic bar has one length of winding, while for the right one has exactly the opposite. So imagine that you let a current, AC current for example, so you magnetize one material in one direction and the other one in the opposite direction. Then take an outer coil, a pickup coil, which is winding both of them, and if everything is symmetric, you got a flux change positive in, let's say, the one of the left, and negative the one of the right. Then nothing you measure at the outer coil. But if we add a DC field, this means that in terms of the AC field, which is magnetizing the two ferromagnets, we see something which is displaced. So consider that the hysteresis loop, the magnetization of our magnetic material, is the purple loop at the picture at the right. Then if we put a positive field, a positive field like that, we would discover, we would see the shift, and the opposite would occur for the other one. So if we have a way to displace in field the two hysteresis loop, it ends up that we magnetize both together in the opposite way as we have done there. We will measure something, but this measurement will be not at the same frequency of our magnetizing current, but will be a second harmonic. So at the pickup coil, we will see an AC voltage where odd order harmonics subtract, but even order sum up. So we have a second harmonic measurement. It turns out that the second harmonic amplitude is extremely sensitive to the magnetic field applied. This is very nice because essentially we have used only the symmetry of the magnetization of a magnetic material. So we use a very highly nonlinear effect, so the magnetization of a ferromagnet, to get some very precise measurement of the field. This flux gate method can be, let's say, exploited by making a very small size. You see the instrument which is there. It is essentially a scalar instrument. So you may have many, one inside the other, to assess the three components. It can achieve a resolution which is really exceptional, like this one of 3 picotesla. Flux gate are, let's say, exceptional instruments, and they are realized to be the sensing magnetic field of many space missions. So they are really state-of-the-art magnetometers. For commercially, there are also instruments that are extremely nice, with very good properties, and as we have seen before, they have the quality of having essentially a null indicator. So you don't need any calibration to detect zero field because they are based on symmetry. So they will give the zero without any calibration. Typically, they are able to measure low fields. So it's very difficult to go below 1000 microtesla, but they were very well below that value. If we want to go above, then it's much better to use another principle. So to use the Hall effect in metals. So why the Hall effect? We know the Hall effect because very often in physics, because the sign of the Hall effect is something that has to do with the sign of the charges. But it's also an effect where the resistivity is proportional to the magnetic field which is applied. So why not to use select some material with a very large Hall coefficient and use it as a magnetometer. So it turns out that this condition is realized in semi-metals and semiconductors. Bismuth is a very good as a coefficient, but also silicon, but indium antimonide as a record. So we can really select crystal, generally single crystals made of this material, to make the probe of instrument capable to measure the magnetic field. The result is an instrument that is very common in labs. It's called the Gauss meter, but they are all effect, let's say, magnetometer in a sense. They can achieve a very good resolution for the full scale. The sensing region can be as small as millimeter. The main point is that they suffer offset and temperature. So there will be always a voltage offset around, and the temperature compensation is critical, and this mainly because they are semi-metal and semiconductor. So there are some electronics, some compensation that has to be cared. But the good point is that they measure the vector component. So component per component is a very practical and flexible instrument, able to cover a wide range of magnetic field from the let's say almost to the microtesla, even not really, up to a few teslas. So really flexible. Other effects that involve magnetic materials are AMR, the anisotropic magnetoresistance of ferromagnets. The point is the following. So forget about the Hall effect for the moment and take a ferromagnet. So in certain ferromagnets, they have these special properties of having a quite large difference in resistivity if the current is applied parallel to the magnetization or perpendicular to the magnetization. And generally, it's the condition of them being parallel that gives the largest resistivity. So if we are able to rotate the magnetic field of 90 degrees, we pass from high resistivity to low resistivity in, let's say, cosine type way. Imagine you want to build a magnetometer. You want to, let's say, use a magnetic field to change a little bit the angle of the magnetization with respect to the current. So you would like to put at 45 degrees. Put the magnetization at the 45 degrees and then use a field which is also at 45 degrees with the current at 90 degrees with the magnetization to make just a small rotation. The point, somehow strange situation is realized by this method, which is called the Barber pole. So researchers have realized a bar where the metal, the bar is the ferromagnet, and then there are metal which is superposed at 45 degrees in strips like that. So the current passes in the metal, but in order to traverse from metal to metal, it has to go down into the ferromagnet, but then the current will be perpendicular to the stripes, and then at 45 degrees with the magnetization, being the magnetization along the main and long direction of the ferromagnets. So with this, it's very easy to have the magnetization and the field perpendicular each other and the current at 45 degrees. in practice, what we have to do is to miniaturize this in a device, so to make a chip where you have some complicated ferromagnetic lines and then superposed by metallic contact. In any case, then you would like to increase the signal, and then you put many of them, but in any case, something can be as small as a chip, and these chips are very commonly used as a magnetic field sensor. The sensing region, again, is around the millimeter. They are very robust because in the end it's just to measure a change in resistance. And these are the typical magnetic field sensors that are used in automation, and for example to measure the position and the velocity of gears and whatever. So most of the classical and cheaper magnetic field sensor will be EMPIR with most probability. Well, the sensing region is very large, so if one would like to have a sensing region smaller, then would like to use some other sensor. Discovery of new sensors of the magnetic field was a very important discovery for magnetists, for the research in magnetic thin films in the 80s, because these two researchers that also got the Nobel Prize by their discovery, they found that if you have a multilayer with alternating magnetization, then you get a resistance which is large, and this large resistance can be decreased if with a magnetic field you make all the magnetization parallel. These layers have to do very small thickness, so we are in the nanometer range. But it's possible to make alternation between ferromagnets, for example iron, and metal like chromium, and to make systems like that. So the principle that was discovered by Friedrich Grünberg was then taken to a different level by engineering all these effects, by using different material, by using just two ferromagnetic layers instead of many, or by changing the spacer between the two from a metal to an insulator, so exploiting a tunnel magnetic resistance. What we got in the end was a very exceptionally working magnetic field magnetometer that could be realized on a size so small, let's say well below the microns, so arriving almost at the nanometer size, that can be put at the very tip of the reading probe of a hard disk, let's say, head. And this has permitted the enormous increase of storage density in the magnetic hard disk that still we have today as storage media. And this was possible because GMR and TMR. So nowadays, also GMR and TMR magnetic field sensors are commercial. You can buy chips with this sensing. So like the AMR, they have similar ranges for the magnetic field, but much slower sensing region. For example, in the sensor Sensitech, found some properties here. So the sensing regions is, let's say, below microns, so really small. Always from the point of view of having, let's say, a view on the typical sensor that we find in chip, we have also to mention that the Lorentz force MEMS chips. These are very interesting objects, quite complicated from the point of view of microfabrication. So essentially the idea is to take a silicon chip and being able to, let's say, to dig into the silicon some mechanical object, able to mechanically move, and then to detect the force which is exerted on the moving part by a magnetic field. So to have an idea, we cannot go too much into the details, but essentially the point is that these moving parts are built and grown into the silicon by some very special method. Then by looking at the change in the resonance frequency, mechanical resonance frequency of these moving parts under a magnetic field, one can measure the let's say, the Lorentz force, and therefore the magnetic field. Very interesting, but well, there are references here on the methods, and also I know that ST Microelectronics is developing this. Let's move on, and now we move to the nuclear magnetic resonance measuring instrument. This is something we have already seen before. So the two nucleus that are generally used are the proton or the nucleus of hydrogen. If this is in water, we call it shielded proton, or the shielded helium. So you have to purify helium in order to get the helium-3 isotope, and then you have the very precise value of the gyromagnetic ratio that can be used for metrology. We already seen that this precision method can be used to make instruments, and especially instruments able to measure at a very high fields and very high fields essentially. But you have to generally, the material is changed, so some hydrogen-rich polymer or rubber is used. What to say about the NMR? Well, essentially that is an incredibly small effect. So the point is that if you take water, essentially water is a diamagnet, and if we look at the nuclear response, and it is not a strong diamagnet, by the way. So if we look at the nuclear response, we see that it's 3 orders of magnitude smaller. So something which looks impossible to measure, as it's completely covered by another effect which is due to electrons that is 1000 times larger. But the point is to exploit the resonance, and the resonance of the electrons and the protons occurs at completely different frequency. So even if the nuclear magnetization is so small, it is possible to exploit it. Also, this we have already seen. This is essentially the system which was developed PTB to measure for the very, let's say, low fields. In that case, the point is to use this called free precession. That is, you just bring the system out of equilibrium, and then you let the magnetization of the proton to relax toward equilibrium, and you will see something like that. So oscillations with damping. For certain material, the damping is long enough to permit the detection of this free oscillation. It turns out to be a very precise method of measurement of the magnetic field. There are also instruments that are designed to measure the very, very low magnetic field by the free precession of proton. This, for example, is a commercial instrument of geometrics. Is an instrument which is able to measure only up to 90 microtesla, but the resolution is exceptional, 0.1 nanotesla. These are the typical instruments that are used in geological prospection, because in that case you just want to measure the very, very, very small changes of the magnetic field around the Earth field. There are different methods to exploit the nuclear magnetic resonance. So this is just to mention that there could be an interplay between the spin and the nucleus and the nuclei, and if you exploit this relation, you can say increase the nuclear polarization. Okay, and with this we stop and we pass the fourth part.